All right, let's get started then. So where we left off last time was started talking about dynamic memory, and I talked about two constructs called malloc and free. Malloc stands for memory allocate. Free is to free up the memory that you allocated. The difference between the dynamic memory and the reason it's referred to as dynamic memory is because it's allocated when the program is running, as opposed to the stack or static memory, and same for global variables, which is actually allocated or decided how much we need to allocate when you are writing the program. When do you use dynamic memory? Typically two reasons. One, you don't know how much memory to allocate when you are writing the code. So I know that I'm going to need an array of integers, just don't know how long. I know that I am going to accept email as an input from a user to the program, just don't know how long it's going to be. So what I don't want to do is fix and say you cannot have an email longer than 50 characters, because if the user does want to use more than 50 characters, I want to allow that. So instead of using static memory and fixing the sizes with assumptions, I want to have the ability to dynamically calculate how much memory is really needed and then use that much memory at runtime. That's the first use case. The second use case for dynamic memory is where there are functions that you have which need to return useful data. And we have so far looked at functions can only return a single value. So it's either a pointer or a single variable. What happens if I want a function to return an array? And that array is not passed into the function because it's not known. So a very good use case of it, what if we want to write a function called prime that actually calculates, and maybe I'll just say int n. I want this function prime to actually return an array, or calculate an array of the first n prime numbers and return a pointer to that array. So what I want is this function actually returning an integer pointer. It's called prime. And I want it to return the first pointer to the first n prime numbers. Very simple use case. How would you actually accomplish that? So either if we did not have dynamic memory, we will actually have to create an array and pass in a pointer to that array. What you cannot do is, and for two reasons you cannot do that. What I cannot do is create an array in here called, say, primes, and say I want to have an array of size n. And then later, just simply return primes. This is actually going to break for two reasons. First reason, we are putting something on the stack. The size is unknown because until the program actually runs and this function is called, we would not know what n is. For all that we know, n can be something that the user is about to type on a keyboard, and then we provide them with a size within the first n prime numbers. N is not known. The compiler is actually going to barf back at you right away. You cannot have something for which the size is unknown on the stack or in the global memory. It has to be specified what the size is when you are writing the program. So you cannot do something like this. Let's just say we come up with a lame way of fixing it. We'll just put 1,000 here and say the program is never going to ask for more than 1,000. I'm making an assumption over here clearly that the programmer is never, someone who is using my function is never going to ask for more than 1,000 prime numbers, right? Just as a best practice, not necessarily related to dynamic memory, but whenever you make an assumption in your code, you can actually insert what we call an assertion. So I'll just put in an assertion saying assert n is less than or equal to 1,000. What does an assert do? It's just a very simple C function. What the assertion does is, if the statement inside the assertion turns out to be the false when the program runs, it crashes the program, and it prints an error saying n was actually greater than 1,000. What's the value of adding the assertion over here? At least, if the programmer asked for more than 1,000, what would happen if I did not have the assertion, and somebody calls my prime function with 5,000 as the argument? My code will still run. I'm going to create 5,000 prime numbers. The first 1,000 will go inside the array. What will happen to the remaining 4,000? They will just override whatever else is there in memory, kind of the example we talked about with Facebook getting hacked with very lengthy email addresses, and a lot of websites used to have that problem. So to avoid that, you want to put an assertion, and this is how you make, this would have been an unsafe code. We have converted it into safe code. If this happens, an error will pop up that you're trying to ask for too many. And at least it's not as good as having a function that could accommodate the large n, but at least it's a lot better than having a function that completely silently fails if n was larger than 1,000. And that's the operating keyword there, silent failure. You always want to avoid silent failures because those are the most painful ones to debug. Remember what I gave the example of the Perl programming language where if I just misspell a word, it would just assume that the value is 0. Horrible example of a silent failure because you have to debug it. It takes hours for you to discover that you missed an E in naming a variable, for example, because it just fails on you silently. So you want to make, if you are making an assumption, you always want to put an assertion. That's something that you want to definitely take away in your toolbox. That does not necessarily only apply to memory, but anytime you're making an assumption in your code, always want to put an assertion right next to it. You'll be surprised, it will help you. Typically, it pays off within the next few hours when you start debugging. Assertions actually are a very good use and very easy to put in as well. So I was able to create an assertion on the fly. That's one way of doing it. Solve the first problem. The compiler is not going to bounce back at us now. And people will be greater than n will actually get a slap back, so that's off our shoulders as well. Does this still work? Is this going to work the way it is right now? Will it? No. So to be very specific, let's actually look at how will somebody call this function from, say, their name. So somebody is expecting to call this, let's say, prime of 10. And is expecting that you are actually going to return like this. Is this a valid program? I have a simple main function and a call to a prime that we know what it is. What's the problem with this?
You created the array inside on the stack, and once the function gets done, it gets cleared out.
So the array, precisely. So the array actually got created on the stack. Scope finished. Remember the 3 things about local variables. Local to a function, which means they are defined inside a function. The second thing was, as soon as we hit the end of the function, they are gone. So the array is gone, but we have actually returned a pointer to that array. And we actually have a bug in our program at this point where this variable a is pointing to nothing. It's just pointing to thin air. It's pointing to something that's maybe there for a short period of time, but it's going to go away as soon as something gets pushed onto the stack next. So how do we deal with something like this? I really want this function to be able to return memory, actually create memory that does not go away. And whenever you have need for memory that is not temporal, memory that does not go away, that's when dynamic memory comes to rescue. So that's the second use case for dynamic memory. So in this case, what I can actually do is, instead of declaring it as int primes 1000 and put it on the stack, here's what I could have done instead. I could do int star primes. So this is a pointer, and equals to malloc. Just to keep it consistent with what we had before, 1000. Always important to keep in mind that malloc, the argument that malloc takes is in bytes. It's not in whatever the type of the pointer is. It's actually the number of bytes that you want allocated. So how many bytes do I actually want allocated in this case? It's I want n, but let's just say we're going with the assumption that n is never going to exceed 1,000. Just
4,000.
4,000. So it's 1,000 times the size of an integer. So the answer he gave was 4,000. What's the inherent assumption that's being made in there?
Oh, it's going to be
that an integer is 4 bytes, making an assumption that an integer is 4 bytes. There are cases where, as I've mentioned in the past, Motorola 68000, if your code is ever running on 68000. By the way, 68000 is an interesting computer in itself. It's actually the most prevalent microprocessor in the world. There are more 68000s than any other processor. You barely hear about it. It's pretty much in every microwave, in every refrigerator, in every car, you have a Motorola 68000 running somewhere in there. And I think the numbers from like close to 7 years ago, an average car had about 300 Motorola 68000s in it. So every kind of computing operation that's happening in a lot of these embedded systems used to be Motorola 68000. It's changing over time. ARM and Intel have come up with competing products. But Motorola ruled the world for nearly 25 years on just having the most prevalent microprocessor in the world. So on 68000, int is actually 2 bytes. So your code would have broken. So there's a better way of doing it while we are at it. And every time you write malloc, keep this in mind. You can actually use the size of function. Remember, that's something we used when I was doing some toying around. You can just say size of int. So I'm looking for 1,000 integers. I'm just going to say 1,000 times size of int. Now, whatever computer I'm running on, the compiler will determine the size of int and just get me that many bytes. I don't have to do that math in my head. And when we'll get to the later half of the semester and talk about templates, that's pretty much the last week of class, this feature will become a really powerful mechanism, in fact, putting it all together. So using sizes as using types as function arguments. So size of is a compiler construct. It's not really a function. It's a compiler construct that the compiler knows the size of int. The compiler has to know the size of int because otherwise it will not know how much space to allocate on the stack. Since the compiler knows the size of int, the compiler will automatically replace it with the correct value. You just say size of int. Always better practice. Never use a constant if you don't have to. And if you are to use a constant, always put an assert. So another way to do what you wanted to do was, I could just do 1,000 times 4, and then put an assertion saying assert size of int is equal to 4. That's another way of getting slightly inferior, but actually a similar solution. So we could do 4,000, but then you're making an assumption. Every time you're writing a line of code, ask yourself, am I making an assumption here? If I'm making an assumption, just don't waste any time, put the assert right there. It will come back and help you. I've talked about some features in the past where I said you won't see the value of it until you've gone out a few years. Asserts is one thing I can tell you, you will see the value of it within the next few hours of putting it in. It'll actually help you in your debugging right away. Because you will have a bug somewhere else in your code that will lead to an n greater than 1,000, and having this in there would mean that your program will actually crash and tell you where to look for where the problem is. You won't have to look through the debugger as much. So that's it. But we'll go with the first solution, malloc 1,000 times size of int. This memory is using dynamic memory, which means it's get allocated on the heap. When something is allocated on the heap, it does not go away. It does not have a scope. The only time heap goes away is when your entire function finishes and your main comes to an end. At that point, you want it to go away anyways. So while you are still writing the function, while the program is still running, this memory will stay. So malloc would mean primes, now a pointer, return the pointer, and now we actually have a working program because it's actually returned a pointer to something that's going to stay. Now, best practice is that when you're done using A, the array that got created, you can actually free the memory by just calling free of A, because I'm no longer using it. So just a quick pros and cons check between stack memory and heap memory. Heap memory is better in that it stays around, it does not go away. You get to control when it begins to exist, and you get to control when it goes away. The downside is the same thing. You now have to decide when it comes into existence, and you have to decide when it goes away, which means if you forget to call the free, eventually your program can run out of memory. You can keep on adding more and more, and eventually your program will just run out of memory. So I have a story on this. In fact, Wall Street, financial industry, obviously, some of the heaviest users of computers out there in the world because of stock trading, all that stuff these days does not happen manually. Very few, it's only amateurs who sit there and deal with web GUIs when you're buying stock. The guys who are making the big bucks are always using computers to make those transactions. In fact, high frequency trading is so performance driven actually, that there's actually a dispute about who gets to sit closest to the stock exchange. So if you have 20 people who are going to be buying stock through their computer and their algorithms are actually making the decision, the speed of light actually matters. That's how fast those trades are happening. So people actually pay big bucks to stay closer to the stock exchange versus farther, because the milliseconds delay or the nanoseconds delay that happen can mean this guy will get the stock before I do, and he's going to end up making more money. So when you're in an industry like that and you're doing high frequency trading, sometimes millions of trades a second are happening. When you're dealing with that, performance definitely matters a lot. And but then all of this is software, so people have bugs, and some of the software has existed for decades, which means some of the bad practices still exist. So one of the things that plagues some of the old software at Wall Street is that people have written a lot of mallocs, but not done a good job of making sure everything gets free. We actually have a name for it. We call it a memory leak. That means you're just leaking memory over time. Every time you do a malloc and there's not a subsequent free for that, you basically have a memory leak. If that program or that for loop that's leaking memory continues to run, eventually you're going to run out of memory. But if you're at Wall Street, you don't have you can't take the chances of going back and trying to fix that code, because if you introduce a bug, that bug is going to cost you a lot. There's actually a horror story around this from 2006, I believe. Knights Financial, can't recall the name of the company, starts with a K. There's a Wikipedia entry on that. If you just search like software bug Wall Street, it'll pop up. There was a company who actually had a software bug that they deployed in high frequency trading. When the day started, the company was worth $450 million. By the time the first 2 hours ended, the company was bankrupt, it was all gone. So that's how expensive a software bug on Wall Street is. The company literally closed its door midday. So with that kind of stakes, you don't want just the average Joe going in and trying to fix your software and adding freeze in there.
They should put some assert in between, you know?
So there's all kinds of coding practices that they've screwed up over the years, obviously. But nobody wants to go back and fix it either. But there are memory leaks, which means so what's as bad as a bug? Probably a little less bad. If the bug is going in and making frivolous transactions, that's the worst thing you can have. But the second worst thing to a bug is when you're fighting and paying money to sit a few nanoseconds closer to the stock exchange. What happens if your computer crashes? That wastes a few minutes, and that's infinity in the world where you're doing 1 million transactions a second. So a minute is worth a ton of money if you actually have to reboot your computer in the middle of the day when the stock exchange is running. So what you don't want is running out of memory. Running out of memory would typically mean the blue screen of death pops up and then you have to reboot your computer. You don't want to be rebooting, you don't want to be fixing your code, so what do? They actually buy computers with tons and tons of memory. Just enough memory that it can get you through the 8 hours that the market is open. And then at 5 p.m. you just go and hit reboot on all your computers and get rid of all the memory that's been leaked throughout the day. Extremely large, extremely expensive equipment, hundreds of gigabytes, terabytes of memory typically put into each one, just to overcome the bug that was introduced that they did not have enough freeze at the right time. So and when your computers run out of memory, it's not the same stakes, hopefully, but it's at least inconvenience, and that happens to all of us on our phones. And on phones have gotten a little better, but laptops it used to happen a lot. Blue screens would pop up, you'd run out of memory. Very important to understand memory leaks. And I mean, this one's actually a classic case where very easily I could have forgotten to do this free. The malloc was done by somebody else inside the prime function that they wrote. I just used I forget to put the free in here, and now we have a memory leak. Now what happens if somebody puts this loop inside of, this line of code inside a while loop? Keep allocating memory, eventually you just get a run out of memory. If it's going to happen 1 billion times, you're trading stock, it's going to run out of memory very quickly. So the answer is not to buy bigger computers with more memory. The answer is to, every time you do a malloc, you have to be very responsible, and that's the downside of dynamic memory. Upside is you have more control. The downside, you have more responsibility. Yep.
So that's basically what we did in Project 2, right? Doing like
You guys are actually allocating memory and creating memory inside the array.
memory pool.
Absolutely. That's exactly what a memory pool is. Yep.
If the A wasn't passed, could we free the memory by saying free prime or something? If A wasn't returned, if if A wasn't returned back?
Excellent question. So if A wasn't returned back, if this is what the code was, I just did this. Well, first of all, you can argue, well, what's the point of having this function call in the first place if A wasn't returned back? But let's look past that, because there are times when that function may have had a side effect that you actually wanted to achieve. This is actually a classic example of a memory leak. Memory leaks typically happen because you create something on the heap. To call free, you have to have a pointer to the memory, otherwise you can't free it. If you lose the pointer, literally lose, in this case we have lost the pointer because we created a variable, you call the function, you don't have a return value, the pointer has been lost. Code down below, even if it wanted to, would not be able to free this memory because the pointer has been lost. And this is typically the number one reason for memory leaks. You lose a pointer accidentally in your code, and you just can't free it anymore. So it would actually be, if I did not have this and this, it would actually be a bug.
Or we could put the free like around the prime.
So yes, you could do the free around the prime, and then I would really argue why do you even have the function call? But
maybe
absolutely. Yeah, so I could have actually done something like this. If prime actually had another side effect, I could do something like that. But the key is, when you're playing with pointers, you have to be very careful. You can lose a pointer very easily. And in this case, it's actually an easier example. When you're dealing with complicated data structures like binary search trees and lists, and you have pointers going all over the place, it's very easy to lose a pointer in that process, and then would have no mechanism to actually free that. So when you're thinking about code, you have to be very careful. And when you're thinking about dynamic memory, so another argument there is obviously that if you know that you're actually going to, before you use dynamic memory, you should make sure that there is no way for me to do this as a stack. If you can do it as a local variable on the stack, it's always preferable, because you're actually just going to end up with better code with less things to worry about. Few lines of code, less things to worry about, less chance that even if you get your code perfect today, some yo-yo is going to come next year and get your code. So if you can do it with stack, it's always preferable. But situations like this do show up where you have to get some data to persist, or you don't know the size. Let's actually go back and improve this code to a suggestion that was made earlier. Remember, we put in this number 1000 and this assumption only because we were using static memory. Now that we are using dynamic memory, we can actually do this. N times size of int. It's dynamic memory, so the heap can actually create that much memory for you on the fly. Because we no longer need to specify the size. It's a function that gets called, and we'll here in a second look at how the heap actually gets used. The kind of issues that you can introduce with this, one of them we talked about is a memory leak. The other kind of issues that you sometimes run into your code is you can do a double delete sometimes. You can have a double delete error. So I do a free, and then I later do another free on the same pointer accidentally. Like if I do, just going back to our old code, if we have a is equal to prime, then we actually do free a here. In fact, let's do it right here, for instance. So I create the array, I actually calculate my primes. I'm not going to write the entire code for that. And then I'm being a very responsible programmer, so I'm just going to say I allocated something, so I should deallocate it. That's clearly a bug. And then you return primes. You get back to the main, and then there's a second free call. The good thing is that the program will crash. It's actually a good thing, because if it did not crash, then you could actually have a situation where you have a pointer just lingering around, which is pointing to nothing. So let's talk about how did this work, because there was a concern, how can you return something? So what is primes here? It's a pointer. It's a pointer to a piece of memory. What happens when you call free? That memory is no longer allocated, it's deallocated. What happens to prime though? You guys know enough about functions to know, can the free function actually change the value of prime here? What gets passed into free? Let's have a quick pop quiz on something we learned last week. Passed by copy versus passed by reference. we are passing in a pointer to prime or passing in a prime? Are we passing in the pointer prime or a pointer to the pointer primes? What is getting passed in here?
Pointer to the pointer prime.
So this is a pointer. Primes is a pointer, which is a variable that's actually pointing to somewhere else in memory. A pointer to this will actually be something that actually points to this value right here. How would I get a pointer to where primes is actually stored in memory? That would actually look like %. I would actually have to get the pointer. If I don't do that, what happens? On the stack, primes actually gets copied over to another place, and then free works off of that. It's just nothing sacred about free. It's just another function call that actually happens and takes care of something on the side. It cannot edit primes, which means that the pointer will stay, the pointer value will stay and continue to be what it is. It was pointing to here in memory, it will continue to point to here in memory. It's just that what it's pointing to is not there anymore. You still have the value, you can still return the value. It's just a variable that gets returned on the stack. Gets out over here. You don't realize that you have a bug until you call the second free. And that's when your heap is going to make the program crash, because you're trying to deallocate something that's already been deallocated. So the typical two bugs again to remember is either so for every malloc you need to have precisely one free. If you have 0 frees, you have a memory leak. If you have 2 frees, you have a double leak. And hopefully your program will crash if you try to do a double, so there will be no such thing as a triple leak. You'll either have 0 or you'll have 2. And either both of those are bugs. The problem with double delete is actually easier to catch, because as soon as you have a double delete, your heap is going to cause the program to crash, and you will know precisely where it crashed. If you actually forget to put a free, the program will continue to run, and it may not run out of memory today, but it might run out of memory when it's running on a computer with less memory like my watch, because it can run out of memory faster on a computer like that. You have a question?
Yeah, so the function free will just break the connection from like the prime pointer to our.
So let's dive into how the heap works. Before I do that, just want to make sure that you guys understand how to use the heap. So malloc and free, those are the two constructs. When you use a malloc, you have to pass in the number of bytes, and what it returns is a pointer to a chunk of memory with this many bytes. Now let's talk about what does malloc and free really do inside. Actually, since some of you said it's beneficial to have a view of what the whiteboard looked like, I can actually take a quick picture here. All right. So
wait, I have a quick question.
Yeah,
I
go
know
ahead.
you just erased it, but you had free primes before you returned the
That's
pointer.
right.
So that's good practice? Or
No, that's a bad practice. I mean, in that case, I created a memory, I freed it, and then I returned a pointer to that memory. So it's as bad as returning something, a pointer to a local variable. Yes, sir.
Whenever you call malloc, and then you said that it returns a chunk of memory with those number of bytes, does it return the pointer to that?
Yeah, it returns a pointer to the top of that. And let's actually take a deeper look at what the heap actually looks like. So what a heap is it's basically a chunk of, or I'd say a segment of memory set aside for dynamic allocation of memory. So dynamically allocated memory always lands in here. The way the heap works, it's basically an array, so very similar to what you guys did in the programming lab that's due tonight. It's basically just a pool of memory. You actually keep track of, so a bunch of memory locations in here, very similar to an array. And then you keep track of which of these bytes have been allocated and which of these bytes have been up for grabs, that anyone can actually grab them. So the way it works is, in fact, it's a very complex subject on how you design a heap. One of the simplest heaps that exist are it's actually called the Knut heap. It's actually one of the simplest algorithms out there. But it's a subject that people have been studying for the last 50 years, so there's a lot of material on how to do the heap and many algorithms, and we'll see in a minute like what makes it complicated, why why it's not something like a solved problem like the stack is. Stack has been a solved problem for decades now, but heap has people still get PhDs on how to do a better implementation of the heap. What we're going to go back to is a very basic implementation of the heap. So a very basic implementation of the heap, the goal is I have to be able to support two functions, my malloc and my free. For us to allocate memory, I have a pool of memory and I want to allocate memory. I have to be able to return a pointer to what gets allocated in response to a particular request when a malloc is called, and then free it when I'm actually done using, when the free is called on the same memory. So let's just start with an example. Let's say this is what our heap looks like. Actually just gonna assign a few spaces, so 1, 2, 3, 4, 5, 6, 7, 8. So I just have a heap with 8 bytes in there, just for the simplicity. Somebody calls a malloc 2. The first 2 bytes are assigned. The malloc actually returns a pointer right here, a pointer to the first of the 2 bytes. Let's say somebody then calls a malloc of 3. What happens then? The next 3 bytes get assigned, and what we return is a pointer to the first byte in that size of 3. Now, let's just say, and in fact we'll just turn this into a little bit of a code here. So I have malloc of 2, and we'll just say A is equal to malloc of 2, B is equal to malloc of 3. So we know that A is now pointing to over here, and B is now pointing to right here. Any questions so far? Now, if I actually call free A, I'm just using the squiggly to represent that this memory is actually allocated at the moment. When I say free A, what happens? A will still continue to point to that memory. It's just that that memory will no longer stay allocated. So whatever is there stays there. It's actually very important to remember that when you call a free, it does not even destroy the contents of memory. All it does is this memory is now up for grabs. Now what happens when I do C is equal to malloc of 2? Which 2 bytes would the heap actually allocate to C? The first 2, because it's up for grabs again, it's no longer used. And so I have A and I have C. A is pointing to the same location, but really for the wrong reason. And C is pointing to the location which is currently in use, but for the correct reason. So when you actually free something, it does not destroy the contents of the pointer. It does not destroy the contents of the memory. All it does is it puts that memory back onto what we refer to as the free list. Free list is bytes in my heap that are up for grabs. So when I say free this, it actually takes that chunk and just calls it free yet again. Just makes it free. And next time somebody looks for memory, you just assign that memory. Yeah.
If you're only passing a pointer into free, how does the heap know how many bytes to free?
Excellent question. So the question is, since we are only passing a pointer to free, how does the heap know how many bytes to deallocate? So first question to you would be, what's the sensible answer in this case? How many bytes should the heap free in this case when we call free to A? 3 of them. 2 bytes. And that's because when A was created, we said 2 bytes. We want the compiler to actually, or the computer to actually deallocate exactly 2 bytes. But we need a place to store that information that this chunk is actually 2 bytes, right? If we have that information stored, that's fine. Where do we store that information? There is actually a construct. So the heap is not as simple as what I drew here. There is a concept in heap. There are 2 concepts called chunks and signatures when we're dealing with heap. So a chunk is what it is. Basically, A is a chunk of 2 bytes. But there's a second piece which I did not draw here called the signatures. And the signatures stores precisely that information. How big is this chunk? So the way we do that, before I go forward, there was a question here. Somebody else? Yeah.
What would happen if you were doing C equals malloc 3?
What happens if C is equal to malloc 3? So, excellent question. You tell me what would happen if C is equal to malloc 3.
So you know to go at the end of B?
Yeah, it would actually end up going right here. And this place will stay empty, this is used, and this is used. Now let me take your example further and say, what happens if it was c is equal to malloc of 1? Where could we expect that to go? Either it could go right here, actually it could go from any one of these locations, but most likely it will just end up being at the top. Yeah.
So can we get the size of like A, or the size of the memory that we allocated for A, if we like ask the user to like enter a value for malloc of like in the previous example you used n to allocate memories.
Correct.
But like say we don't know that size, but we want in some part of the program we need that size. Can we find the size of A?
That's an excellent question. The de facto answer is you cannot. You have to know like how many bytes you allocated. You're expected to know that, and it's usually a function of some variable, some other variable, just like we did in that case, which was n times the size of int. So you have to remember that there are some advanced features we won't get into 3.12, but you can actually query the heap at a lower level, and it will tell you how many bytes they're really stored for a particular chunk. It's actually possible, but it's not like a common thing that you would use. Typically, you just interact with the heap with two functions, malloc and free. Yeah.
What will happen if you have this segments of like 2 or 3 bytes just spread out across and just like 1 or 2 left in between? Throughout the memory, the entire memory is occupied, but if you look, there are many segments in between. How would, I mean?
That's a great question. So what happens if over time, as we talked about, and this was the point you brought up, which is if you had a malloc of 1, it would have gone right here. So malloc of 1 goes right here, a malloc of 3 went right here, a malloc of 3 went right here. You have 1 byte sitting in the middle. Let's say then you free C, and this begins to exist again. How many bytes do we have free in total? We have 3 bytes down here and 1 byte down here. 4 bytes. But what happens if a malloc of 4 comes in? Can I just say you get 2 pieces, 1 here and 3 down here? Malloc's always going to return a contiguous chunk. So even though there's space in memory, it's actually going to come back and say, tough luck, don't have memory for you. And that can happen, by the way. Malloc can actually return an error just saying out of memory, and that's how you detect it. So what has happened here, there's actually a name for this. We call it fragmentation. So over time, you can actually have fragmentation where I have a lot of free memory, but it's just fragmented into small 1 or 2 bytes here and there, which means I may have 50% of my memory free, but not individually, neither of those blocks is big enough to accommodate a large chunk that the user is requesting from me. So in that case, you can either return, the traditional heap would just return an error saying, no donuts for you, you can't deal with that. A better heap implementation, and this is exactly why the heap implementation has been an unsolved problem even in 2015. People have been researching it for decades. How do you actually solve that problem of fragmentation? How do you do it optimally? So one option is if you run into that and I have a byte here and a byte here and a byte here and I need 3 bytes to exist side by side, I can move things around and create those 3 bytes. That's one option. Very expensive, obviously, if you keep doing that. So the approaches that people take, there's a whole body of knowledge around generational heaps and how you actually do it so that first you try to avoid fragmentation from happening, and if you do get fragmented, how do you actually defragment it in a way that it's optimal? Way beyond the scope of 3.12, there's actually an entire course, a graduate course in the CS department on how to work on this. Professor McKinley, actually, she is the one who specializes in the heap and generational garbage collection and all that stuff. So it's a body of knowledge in itself. What we're going to deal with in this class, if you run into that situation where you have fragmentation, well, tough luck, bad, but you just get an error back saying that you do not have enough memory left. So so we talked a little bit about signatures and how does that work. So let's go deep into this. I wish life was as simple as the way I drew it. It's actually a lot more complicated. So the way it works is, let's say we have a heap of 8 bytes. All right, so 8 bytes, yep. Sure.
Can we increase the size of the A or?
Can we increase the size of it later? No, you have to actually remove delete what you created, create a new chunk, and copy everything over. Yep.
Quick question. What's that word next to heap?
Knut, K-N-U-T-H. It's the name of
Okay.
a very celebrated scientist, computer scientist, Donald Knuth. Alright, so the way we do it is, and the way signatures work to a question earlier, we allocate some bytes, and another simple way of saying it is that we actually end up wasting some bytes of our heap in saving that information, which is how big is each chunk. So if you have an 8-byte heap, what we do is we actually save 8 in the first byte and the last byte. And when we I lied, to be honest. I'm oversimplifying it a little. Actually, what you end up saving is a 6. What does the 6 mean? This is one chunk of memory with 6 bytes in it. 1, 2, 3, 4, 5, 6. We had 8 bytes. What happened to the other 2 bytes? They got wasted in saving the signatures. Make sense? Now, this is an unallocated 8 bytes. Now, malloc of 2 gets called on this heap. How does the heap work? The heap goes to the top. You have a pointer to the top of the heap. You see 6. So I have a chunk of 6 available here. I'm only looking for 2. So what do? I take these 2 and allocate both of these to A. A now starts to point right here. I allocate this to A, and then I'm going to have this. I'm going to have new signatures. Just going by my convention, if this was 6 here, how many bytes do I have between this signature and this signature? So this is going to become a 2 and a 2. That means I have a 2-byte chunk sitting here up for grabs. And what about this guy? It's also 2 bytes in between. So I need to save 2. How do I indicate that these 2 are in use and these 2 are up for grabs? I just do a very simple mathematical trick. I just put a negative sign in front. I save the value -2 and a -2 to indicate this is a 2-byte chunk but in use. And this is a 2 bytes chunk but not in use. Just using signatures. So to answer the question that came up earlier, how does the heap know how many bytes to delete? Well, when you pass in delete free A, what does the heap do? The heap has a pointer to A. The heap knows that right before this pointer is the actual size of A saved in memory itself. So it just does a pointer -1, grabs the size from the signature, and removes that many bytes. Answer your question? How many bytes do you see wasted over here? Quite a bit of them. And that's exactly why the Knut heap is not something that everyone uses today. But it's actually a really simple way of doing it for conceptual reasons. Yeah.
So if you call free right after that, would it go back to being a 6 file, or would it stay as 2 and a 2?
So that's a great question. So let's actually do that. So right after this, free of 2 is called, free of A is called. You pass in the pointer over here. The heap actually looks up and says -2. -2 means it's a chunk of 2 bytes, but it's actually a used chunk of 2 bytes. So I'm just going to turn this into a 2 and a 2. I did not delete anything from here, but what this does is now these bytes are available up for grabs. Now there's a subsequent question. I have a 2-byte chunk here, which is free, and I have a 2-byte chunk here, which is free. Do I then combine them, or do I just leave them as two chunks of 2 bytes? Anyone know the answer?
You leave them.
So one option is you leave them. The other option is we combine them. What are the reasons? Let's actually, rather than looking for an answer, let's look at the reasons you want to go one way or the other. So what's the reason to leave them as is?
No, I thought traditionally people leave them.
Yeah, so it's you can actually leave them, in fact, and you can also combine them. It's definitely a choice that you carry. The pros and cons are if you actually want to if you combine them, it's a little bit of extra work that we have to do right here. You just freed something up, you realize, it's actually very easy to check though, because you already are at this memory location and you just checked that it's a free. You can just easily check if the next byte is a positive or a negative. If it's a negative, you leave it alone. If it's a positive, you know that you have an opportunity. What you can do is, go back 2 locations from here, and the 2 comes from the fact that this is a 2, and go back 2 locations from here, because this is a 2, and replace both of these with a 6 and a 6. What's the upside of doing this? You remove some of the wastage. Now if somebody comes looking for a 4-byte chunk, you can handle it. Had we left it the way it was earlier, you would not have been able to handle a request for 4 bytes. So this is one mechanism you can actually reduce some fragmentation that happens over time. Yeah.
Does it erase the signatures?
Sorry, say it again?
Does it erase the signatures in the middle?
Yeah, so in that case you will erase the signatures in the middle. Actually, in fact, take that back. Do you actually care if the signatures stay in the middle or not? No, because when the top one says 6, your heap is not going to care what's in between. It's just going to, 6 bytes, take it. If somebody needs 6 bytes, they get the 6 bytes. Doesn't matter what there is. But the key things to remember, and just follow up to your question, is that in the heap, you never want to assume how a thing is going to be laid out. So a good programmer always assumes that I've called free, and whatever was there is gone, even though it's not gone in theory, because nobody went and deleted or cleared these bytes out. It's never gone. But a good programmer will always assume that it's gone, and will never make an assumption about if these things are going to be side by side in the heap, so I can just jump into the next one or something. When you call a chunk, when you call malloc, you get this many bytes. You don't care what the addresses are. Ideally, you don't even want to know what the addresses are. Because next time you run your program, you might get a totally different set of addresses just based on what the heap state looked like at that point. So never want to make an assumption about heap addresses, never want to make an assumption about heap values. You call malloc, you get a chunk, you use the chunk, you get rid of the chunk at the end. You never want to know, you really don't want to know where it's laid out in memory and want to make any assumptions about what the pointer values are going to look like. Yeah.
Can we use free without any parameters to free up the whole heap?
No, there is no such thing as, you can't actually free up the whole thing. You have to pass in a pointer. Yeah.
Can you like put a malloc 2 and then again put a malloc 3 and then what happens then if you use
So I do this.
before free.
Before free, sure. So we'll just do a is equal to malloc 3. So I have a is equal to malloc 2 and then a is equal to malloc 3. And then I call free a, let's say.
And does it free?
Alright, so, and the question is, does it free this chunk or this chunk, right? So free of a, how does free work again? Free works, you go to, so if we did a 3, so it goes to the pointer, it subtracts 1. That's how it knows how big the chunk is. What is A actually pointing to right now? The 3-byte chunk or the 2-byte chunk? So what's gonna get removed? The 3-byte. What happened to the 2-byte chunk?
It's lost it.
I actually lost the pointer. It's a memory leak. That's exactly that's a classic definition of a memory leak. You created something, you forgot to free it, now you have lost the pointer. Here in the code, even if you wanted to, you can't get this value back, it's gone. But the chunk that you allocated, that one's gonna stay because nobody called free on it explicitly. And that's exactly why you need to be very careful with dynamic memory. That's how most people lose their pointers, is by overriding the variable, freeing the second value, forgetting that there was earlier a malloc that they never freed.
Is our our heap variables global in scope, or I mean they just go after the
They just stay. So it's a chunk of memory, you get a pointer. The pointer can be local or global, however you want to have it. But you have to pass the pointer around if you want different functions, like you were doing with the primes. You
so
have to
it
pass
won't, the pointer itself won't exist outside the function.
No, the pointer is just a variable on the stack. It's just pointing to something on the heap. But the key is that this is chunk of memory that never gets deallocated. So just a couple of more conceptual things to take away about the heap. One of them is that we typically do not build the heap with 1-byte chunks. Like it's not really, we don't think about them as a single byte when you're building the heap underneath. Part of the reason is this. Notice that the signature is just 1 byte here, right? How big of a heap can we actually support if this was 1 byte? What's the maximum size on the heap? What's the biggest integer value I can store in a heap? In an 8-bit, in a single byte, what's the maximum integer value I can store in a byte? What's that?
256.
So, great question. Signed or unsigned? That's the right question to ask. Signed or unsigned, you tell me, based on what we saw earlier. It will be signed because I was using negative values. So what's the biggest size of the heap if I use a single byte for this? 128. You cannot have a heap bigger than 128. 128 is a very small size when you have a laptop which has gigabytes of memory on it. So what we typically end up doing is individual heap chunks are not really a single byte. We typically use larger granularity. Just for the sake of argument, one possible value is that it's an array of integer, and each one of my chunks is 4 bytes. How big can my heap be now? Just out of curiosity. If my signature is going to be stored in a 4-byte value and I'm going to view the world as 4 bytes for everything, how big can my signature be? How big can my heap be? Because now I can support a signature much bigger than before. Right? Earlier we said signature cannot exceed 128.
2 raised to 16.
2 raised to the 16. Why do you say 2 raised to the 16?
2 raised to 32 would be unsigned.
So that's good. So 2 raised to the 32 is the unsigned. What happens when you support signed and unsigned? It halves it, right? If we went from, so what happens when you do 2 to the 32 divided by 2? What's the answer?
Oh, 31.
2 to the 31, not 2 to the 16. Exactly. 2 to the 31. What's 2 to the 31? What's 2 to the 30 first? That's the easy one. So 2 to the 10, what's 2 to the 10?
104.
So what is, if I just forget the 24, 2 to the 10 is 1,000. What's 2 to the 20?
10 is
It's 1,000 times 1,000. What's 1,000 times 1,000? That's a million. 1,000 times 1,000. 1 with 6 zeros. 2 to the 20 is a million. What happens if I add 3 more zeros at the end of a million? Take a million and multiply it by 1,000. A billion. So 2 to the 30 is a billion. 2 to the 31, how many billion is that? 2 billion. It's 2 to the 30 times 2. That's one way of writing it. 2 to the 30 is a billion, so 2 billion. That's how big my heap can now be, except we actually put another caveat, so you can make it even bigger than 2 billion. When you count, since everything in the world is now 4 bytes to us, that's what we decided to make. It doesn't make sense to count in terms of bytes anymore. It just makes sense to count in terms of 4-byte quantities. So if I see a heap that actually has a 2 here, I'm just going to leave 2 blocks and I have a 2 here. Does it actually mean I have 2 bytes here or more than 2 bytes here? I have 2 times 4, I have 8 bytes in the middle. So if the maximum value I can have here is 2 billion, which is what we all agreed that 2 billion is what I have. Obviously this line does not exist. How many locations will I actually have in the middle if it says 2 billion on top and 2 billion at bottom? 8 billion. It's actually 8. So I have 8 billion bytes. In computer language, by the way, what does 8 billion mean? How many bytes is that? How many, if I go with kilo, mega, giga, how many bytes is that? What's a billion? So a billion is giga, actually. So it's actually 8 gigabytes. That's how big our heap. That's the maximum size of the heap that we can have with this scheme. If I wanted a heap bigger than that, what could I do? Instead of 4-byte chunks, I can just deal with 8-byte chunks. I can expand the size of my heap quite a bit by doing that. But going back to the 4-byte chunks, the maximum size of the heap at 8 gigabytes. So how does the heap start? It starts with 2 billion at the top and 2 billion at the bottom. Right? Somebody asks a malloc 2. How many chunks will I allocate for a malloc of 2? How many chunks get allocated when someone asks for 2 bytes? 1. So remember that the chunks are 4 bytes each now, just because we did not want to limit ourselves to having a heap that's only 128 bytes. So we went with a heap where the chunks are 4 bytes. How many? So what if I call for a malloc 1? How many chunks will get allocated here? So you actually get 1 full chunk. You get 4 bytes. 3 bytes wasted. But advantage of that, you can have a much bigger heap now. If you only had a heap of 128 bytes, you would be really tight on every single byte. When you have a heap with 8 billion bytes, 3 bytes is it's not that big a deal if you waste 3 of them. So malloc of 1, malloc of 2, same thing, you get 4 bytes. When you actually have, say, a malloc of 10, how many chunks will I get for a malloc of 10? 3. So let's actually try to create something something that we can actually deal with in our head, so let's not deal with 2 billion. Let's deal with a simple heap which is just 32 bytes. How many chunks is that going to be at 4 byte granularity? 32 byte heap. How many chunks is that going to be? 8 chunks. We're going to start with a 6 and a 6. Same way. One key difference from last time, the chunks are no longer 1 byte, they're actually 4 bytes. Right? Now what happens when I do some similar code here, so I'm just going to do a is equal to malloc of 1. When the malloc of 1 is completed, what will the heap look like? So how many chunks will be allocated for A? 1. Which chunk is most likely to get allocated for A? The top one. So A will start pointing to over here. How will the signatures be updated? 1, 1, and somebody's saying the right thing here. It's not really a 1, it's a negative 1, because this is indicating that the chunk is actually in use. And then we have 1, 2, 3, so it will be a 3 and a 3. This is what my heap looks like after I do a malloc of 1. Now let's say we have a malloc of 5. How many chunks will get allocated for B? 2. So what that means is we're actually going to end up with 2, negative 2, 2 chunks, negative 2, and B will actually point to right here. And basically at this point we have run out of our heap space. You just have 0 down here. And your memory is full. Now let's say you actually do a free of A. What actually happens when we do a free of A? What will the state, how will the signatures change? First of all, are signatures the only thing that's going to change, or is data going to change as well when I call free? Only signatures are going to change. Which signatures are going to change? The first, this guy. So we're going to go to A and do a -1 and get this. What does it change? Change it to positive 1. And when it changes this to a positive 1 as well. So now you have a 1 byte chunk sitting at the top. See the fragmentation problem though? You have a 1 byte at the bottom, 1 byte up here. If somebody asks for 2 bytes, you're just going to have to say I don't have 2 bytes. In reality, you do have 2 bytes. But that's the fragmentation issue. Going back, so +1 here, +1 here. Whatever value A was is still going to be there. A is still pointing to that value. If I do a star A, I will even be able to access that value right now. When will this value get overridden? When next time someone calls a malloc and this chunk gets allocated. So it's another one of those silent failure situations. You can accidentally free something, continue to use it, and at a later point in time it'll blow up on your face. So you have to be very careful when you're actually calling this, using variables that are coming in from free, that you have actually freed. Now let's go to another piece, which is, I want to also free a B next. So I have B right here. It's got a -2 and a -2. Everything is fine. B is pointing to right here. What happens if I actually try to do a free, but instead of doing a free of B, I just want to be a little fancy and I'm just going to do a free of B +1. What does B +1 point to, first of all? So that was a bit of a trick question. So the first knee-jerk reaction is accurate, pointing to the next chunk. But what's the assumption you are making when you say that you're going to actually point, B is going to point to over here when I do B +1? Go back to pointer arithmetic that we learned a couple of weeks ago.
That B is a 4 byte address.
So what information do you guys need to really answer my question? Let's say it that way. What's the type of A and B to decide what's B +1? And I'm just going to surprise you a little and say B is actually a character pointer. So if B is a character pointer, then what happens? What does B +1 point to? Just the next 8 bits. So it's actually going to start, instead of pointing to this first byte, and B is just going to start pointing to the next byte. What happens if I call free on B +1? What's the heap going to do? Does the heap have any way of even knowing that this is actually pointing into a middle of a block? Not really. So the heap is just going to do b minus 4, just get the 4 bytes, and then try to interpret whatever is there and try to free it up. Right? The heap is just going to say, I'm right here, I'm just going to do minus 4. Whatever is contained in these 4 bytes is whatever the heap is going to try to use as a signature. How is the heap going to know that this is actually an invalid free? It's going to take that signature, add to that value, and look for the other end of the signature and see if they actually match. Because remember, these two always have to be equal. You're doing an invalid free. The heap is going to see that those two are not going to match, and it's just going to come back with you trying to call an invalid free. You're not calling free on a valid pointer. And it's going to be. So, very critical to realize that when you call malloc, you have to call free with the exact same pointer value. If you point it with like that plus 1 or something, the heap's not smart enough to realize what you're looking for. It's just dumb. It's just doing a minus 4 and getting the signature from there. And then it's smart enough at least that it's not going to just deallocate random memory. It's actually smart enough to throw an error back at your face saying your signatures are not matching.
So if it's a positive number,
If it's a,
okay.
so,
It's just gonna throw an error.
yeah, so let's talk about that. That's a great question, in fact. What if I actually had a double delete bug? So I'm just gonna, that was not the intent here, but, so what happens if we call another free A at this point? What's the heap gonna do? So I have a free A, I've already freed it. So first of all, it's a double delete bug right away. You see a free and a free do the same thing. But how is the heap gonna detect it? What is A pointing to at this point?
Still.
Over there. What is A pointing to when we call the second free? Still pointing to the same thing. The heap's going to say, okay, free for this memory location, subtract 4, get to the top of the signature, and it's going to see that the signature is a positive value. What happens if you're trying to call free with a chunk that has a positive signature? It's a double delete issue. So the heap's going to complain right away and say it's a double delete. Yep.
So if you, okay, so instead of 43, you allocate those bits, you do like C equals malloc 1, and then you do A. Technically that would work for you, because then it would check and say, see that's already allocated.
That's an excellent point actually. So we did A is equal to malloc 1, we did B is equal to malloc 5. Now let's say we actually did somewhere between this error that we introduced just to show something, and the second free, if I actually had another line of code saying C is equal to malloc 1, where will this C go on our heap? In fact, there's only one place it can go. So C will actually start pointing to right here, and this value will become a -1 and a -1, right? So C is now pointing here, A is now pointing here. Then you call free of A. Does free have any way of knowing whether you're calling it on A or C? It does not. It's just going to say, I have a pointer, -4, and with A, you now are going to deallocate C. Now you try to use C, and it's just going to freak out at you. Double delete bug gets introduced, and it's actually another very common error that people make, where you have a dangling pointer, you free that pointer, it just happens to free correctly, but now you've actually deallocated something that you did not mean to deallocate. So if I call it free of A, it will actually deallocate C. And very important for that reason that you do not use a pointer that you have already freed. So what's the right place to put pointers then? Typically, just as a best practice, you want the pointers to go away as soon as you're done with them as well, so you can't even accidentally use them. Best to actually put the pointers as local variables. You don't want to use global variables for pointers, for example. Because if local variable function finishes, pointer goes away, I don't want to see it anymore. Because if I see it, I'll probably use it, and if I use it, I'll probably create some kind of an issue. Again, another reason for never trying to use global variables. And global variables do actually cause half of these errors because of that reason. Kind of like the example we constructed here. Alright, so we'll pick up with structs next time.
Like literally, I set up a
delete the pointer?
I'm sorry, say it again?
Can't we just delete the pointer using like delete?
Just